Okay, 6-8, number 10. This is a problem with a guy and a kid in a wheelbarrow. And the guy is wheelbarrowing, apparently now it's his daughter, around the yard. And they encounter a brick. And they have to get the wheelbarrow up and over the brick. Now, I got a lot of personal feelings about this one because I used to do a lot of wheelbarrowing around my yard growing up, either helping my dad landscape and plant trees, or me and my brother used to have a BMX track in our backyard where we probably had, I don't know, 50, 60 jumps that we built ourselves. So got a lot of experience wheelbarrowing, and every time I encounter this problem, it's very cringy for me because the person doing the wheelbarrowing is doing the exact wrong thing if you want to get your wheelbarrow over a brick or a rock or up a curve or anything like that, because they're pushing down at an angle along the handles, which actually pushes the wheelbarrow down into the brick, causing a torque that won't let it rotate up and over the brick like you want. What you want is your wheelbarrow to rotate on that corner of the brick up and over, but by pushing any amount down, you're causing your wheelbarrow to want to rotate down and not go over over the brick. So from personal experience, I know you do not want to push parallel to your handles. What you want to do is push forward and pull up on your handles to help alleviate some of that weight causing a torque and get that wheel to rotate up and over that brick point. So this one gets a little complicated. The easiest way to do it is to break everything into X and Y components so that we can do our cross products relatively easily. Our force component in the X will match up with our Y and vice versa. So first diagram here is simply the geometry of the problem, right? We got our brick with height H, we got our wheel with radius R, and if we have contact with the brick, that's R away from the center of mass. So we're going to need that X and Y component from the point of contact to where all the forces are acting. So this is going to be our axis of rotation because we want it to rotate up and over the brick at this corner. So we're going to need this Y component and this X component so we know where the forces are being applied and we can do our cross products. So the first part's easy. Y is just radius minus H, right? If this is R and we take away H, we're left with Y. So that's it. Y is R minus H. The next part gets a little tricky. It gets messy. It just makes the whole thing look terribly messy. So X, right? We got our Pythagorean theorem here. So X is R squared minus Y squared square rooted. But then we know Y because they only give us R and H. So we got to put everything in terms of R and H. So then we know Y is R minus H. We got to square that, FOIL that out. That actually cancels out our R squared. And we get X equals 2RH minus H squared, all that square rooted. So keep these in mind. Write them down before we move on to the next step or whatever, right? Y component of our lever arm is R minus H, and our X component for our lever arm is 2RH minus H squared rooted. Okay, so that's that first part, just geometry. Let's look at the forces, and we're going to ignore one of them. This gets a little messy. So we've got our weight force of the wheelbarrow and the kid in there acting down mg. That's going to create a torque about R. And we've got our force parallel to our handles acting at theta. We're also going to model that as acting at the center of the wheel. But we're going to break that into X and Y components. So we've got F of X. And we got F of Y, and again, we're just going to be pairing up our cross products so our X and Y's will match up being perpendicular. So then we also have a normal force here at the point of the brick because the brick is definitely being pushed by the wheel, and so the brick pushes back on the wheel, and that's part B of the problem, is to figure out these forces here. We're also choosing that as our axis of rotation so those forces don't cause any torques, right? So we can ignore those forces until we move on to the next part. So that's our axis of rotation. We can ignore that normal force. It won't apply a torque. We're also going to make this normal force here with the ground because the goal is to get this to rotate up and over the ground. And that's what we're trying to find. We're trying to find the force here that will get this thing to start to rotate up. So we're finding F such that we're just about to lose contact with the ground and the normal force there goes to 0. No longer applying a torque. All right? So the sum of torques then is our X component of our force matched up with our Y lever arm. I'm going to call that positive because I want it to rotate up and over. That's going to be my positive direction. And this component is the only one causing it to rotate up and over. So I'm going to call that positive. Like I said in the beginning, pushing down with this Y component is the opposite effect of what you want. That's actually going to create a negative torque, causing it to want to rotate in the opposite direction, and we're going to call that a negative torque. So we've got our Y component, but we're going to match that up with our horizontal displacement, doing our cross product. So F of Y times X. And then we got our mg applying a torque. It's what's keeping the wheelbarrow from going up and over the wheel altogether, or up and over the brick altogether. So we got our mg. It's vertical, so we're going to pair that up with our horizontal lever arm, just X, right? Everything is really with a lever arm of R, but since we're cross-producting, we're using the X and Y components of R as we saw in the first diagram, right? So our lever arm really is R for all the forces, except a cross product, we're just using X and Y components based on our forces, right? So here, instead of just doing like finding one component that's perpendicular to the lever arm, or finding the component of the lever arm that's perpendicular to the force, we're breaking everything down into X and Y, and we're cross-producting that way and then adding everything up. So hopefully that makes sense. X force paired with Y lever arm, Y force paired with X lever arm, and then our vertical mg paired with our horizontal lever arm X. Boom. Set that all equal to 0. Put in your components instead of f of x and f of y. Put in your cosine theta and your sine theta appropriately, and solve for f. All right. Hopefully that makes sense. I felt like I went through that really fast, but it's YouTube, so you can play it at half speed or rewind it. Boom, boom. Okay, last part then is to figure out that normal force from the brick. Now we can't ignore that, but that means we're going to sum up our forces x and y. They actually asked us to do that instead of saying like find the normal force. They just said find the x and the y components. So that means all we got to do is add up our components in each direction. So we've got our f of x force component minus the normal force in the x. I'm kind of conceptualizing here. I know the directions of the normal force, right? If I'm pushing into the brick to the right, then the brick is going to push back on my wheel to my left, so negative for that one. Which means the horizontal components are equal for our normal force in the x. So whatever f cosine theta is, boom, that's your normal force in the x. I didn't go ahead and put in f because it gets really long and kind of nasty, which is maybe one of the hardest parts about this problem, is just getting everything typed into WebAssign the right way. So keep that in mind. Make sure you're using all the right variables. Yeah. And then same thing in the y direction, sum up those forces. The wheel has some weight above the brick, so I know it's pushing down on the brick. The brick in turn is pushing up vertically. So I got my positive normal force in the y, and then weight force is down, and then the y component of the person's pushing force is down, negative. Set that all equal to 0. Solve for normal force. It's just mg plus that component in the y direction from the person's push. And again, I didn't substitute in f here because it gets really long and nasty and I'd need like 5 whiteboards. But you can do that appropriately and make sure you're using all the right variables when you type it into WebAssign. Hey, and I don't know, it's you're quarantined at home. There's lots of yard work to do. Maybe go try to push a wheelbarrow up over a curb or a brick. See what happens.